So what would you expect if that object were spinning at more than 300,000 km per second? If an object rotates at a speed exceeding 300,000 km per second, various outcomes can be expected depending on the mass and rotational velocity of the object. Firstly, if the mass of the object is sufficiently large, parts of the object located far from its center will experience centrifugal force due to rotation. This centrifugal force increases with the mass and rotational speed of the object, eventually leading to the object's disintegration. For instance, if an object with a mass of 5.972 × 10⁻24 kilograms, similar to Earth, rotates at a speed of 300,000 km per second, parts far from the object's center will experience a centrifugal force of approximately 2.4 km per second. This centrifugal force is roughly 100 times the gravitational force on Earth's surface. Consequently, such an object would eventually break apart. On the other hand, if the object's mass is sufficiently small, the rotation of the object can cause it to swell. This phenomenon occurs as the centrifugal force on the rotating object's surface causes the surface to bulge outward. For example, if a 1 kilogram object rotates at a speed of 300,000 km per second, the object's surface will inflate by approximately 1.5 millimeters. Although this amount of swelling may appear very small to the naked eye, it can influence the structure of the object. When the rotational speed of an object is fast enough, the object can move at speeds faster than light. This phenomenon involves parts of the object located far from its center moving at speeds exceeding that of light. For instance, if a 1 kilogram object rotates at a speed of 300,000 km per second, parts far from the object's center will move at a speed of approximately 2.4 km per second, which is about 0.8% of the speed of light. Therefore, when an object rotates at speeds exceeding 300,000 km per second, various outcomes can be anticipated based on the mass and rotational velocity of the object. The object may disintegrate, swell, or move at speeds faster than light. If the net is metal, wouldn't a strong magnetic field be generated in orthogonal directions? Yes, if an object, particularly a metal one, rotates at speeds exceeding 300,000 km per second, a strong magnetic field can be generated in the orthogonal direction. This phenomenon is known as the Artemis effect. The Artemis effect was first discovered in 1969 by American physicist Richard Rose. In his experiment, Rose rotated a metal ring at a speed of 10,000 km per second and observed the generation of a strong magnetic field at the center of the ring. The cause of the Artemis effect lies in the current generated by the electrons in the metal. Due to centrifugal force on the rotating object's surface, electrons are pushed outward. These electrons flow toward the center of the object, creating a strong magnetic field. The intensity of the magnetic field generated by the Artemis effect increases with the mass of the object and the rotational speed. Therefore, if an object with a mass similar to Earth, 5.972 × 10⁻24 kilograms, rotates at a speed of 300,000 km per second, the magnetic field intensity at the object's center would be approximately 100 times that of Earth's magnetic field. The Artemis effect has significant implications for the design and operation of spacecraft and space stations. Many metal components are used in the construction of spacecraft and space stations, and the Artemis effect can lead to the generation of strong magnetic fields in these components. This magnetic field can influence the control systems of spacecraft and space stations and, in some cases, even damage them. Therefore, when designing spacecraft or space stations, it is crucial to consider the Artemis effect and minimize the impact of the magnetic field on components.